You might think a fixed offshore platform just sits peacefully resting on the seabed. But in reality, it is locked in a massive, unseen battle against the harshest environment on Earth. Welcome to The Explainer. Today, we're going subsea to uncover exactly how engineers and divers keep these towering steel giants standing against the relentless forces of the ocean.
Okay, here's our dive plan for today's explainer. We're going to cover the underwater threat, surviving the splash zone, deep dives and node inspections, flooded member detection, and finally, scour and cathodic protection.
Section 1. The Underwater Threat, the Invisible War. From the very second one of these massive steel jackets hits the water, it starts deteriorating. It's almost like an iceberg, right? The bulk of the structure is completely hidden beneath the waves. You've got the splash zone right near the surface, and below that, this wildly complex network of legs, nodes, and cross bracings reaching all the way down into the mud. And down there, the steel is facing a relentless, three-pronged attack. We're talking constant fatigue cycling from literally millions of pounding waves, hyper-aggressive saltwater corrosion, and heavy marine biofouling. Just thick, suffocating layers of barnacles and seaweed. Obviously, the stakes of a structural collapse are catastrophic. So these inspections, they aren't just suggestions. They are legally driven by super strict international standards, like DNVGL and API RP2SN, plus specific flag state requirements just to make sure the rig actually stays safe. Moving on to Section 2, surviving the splash zone, the most aggressive area. So technically, the splash zone is defined as the area between the crest level of a massive 50-year storm wave riding on the highest tide all the way down to 3 meters below the lowest tide. But for practical purposes, just think of it as this alternately wet and dry zone roughly 5 meters above and below the normal waterline. If you compare this area to the fully submerged lower jacket, it's like night and day. The deep water is relatively stable, but the splash zone? It is constantly blasted by oxygen, heavy UV radiation, and incredibly violent physical wave impacts. Even if you use the absolute best heavy-duty paint coatings or even copper-nickel cladding, this specific area still requires intense, frequent inspection just to survive. Now, 50 to 100, that is the tolerance in millimeters for marine growth thickness before a cleaning program is absolutely mandatory. But in highly productive waters, it gets wild. Divers frequently run into 20 to 30 centimeters of rock-hard barnacles and mussels. So before an inspector can even look at the steel, divers have to endure this grueling physical labor. They're literally down there stripping this heavy growth away by hand with scrapers and high-powered wire brushes. All right, Section 3, deep dives and node inspections. Into the murk. Whenever we do a deep dive, it usually kicks off with what's called a general swim-around survey. This is done by divers or ROVs, remote-operated vehicles. Basically, before they start hunting for microscopic cracks, they just scan for the obvious stuff. We're looking for impact damage from supply boats, missing structural items, or super dangerous construction debris, like heavy scaffold poles or gratings that might have been dropped and are just littering the seabed. But our main targets, down in the dark, are the structural nodes. A node is essentially a heavy-duty intersection where multiple steel pipes meet and are welded together. Because of their complex geometry and the sheer immense load they carry, these welds are the absolute most highly stressed, fatigue-critical locations on the whole jacket. If the platform's going to crack anywhere, it's probably going to be right here. So how exactly do we inspect them? Well, it's this incredibly intense, step-by-step physical process done completely underwater. Step 1. The diver takes a powered wire brush and blasts away all the marine growth until they hit bright, shiny metal. Step 2. They do a close visual inspection, just using their naked eyes. And finally, Step 3. They bring in advanced non-destructive examination, or NDE techniques, to hunt for those sneaky, microscopic cracks that the human eye literally can't see. And one of the coolest NDE methods they use is magnetic particle inspection, or MPI. Check this out. The diver actually sprays the weld with a white background paint, applies a strong magnetic field, and then coats the whole area with black iron oxide particles. If there's even a tiny microscopic crack, it disrupts the magnetic field and all those black particles gather right at the flaw. It acts just like an X-ray for the surface. Invisible defects just vividly pop out as a clear black line against the white paint. It's amazing. Section 4. Flooded member detection, the internal threat. Okay, I want you to think about this for a second. These massive jacket legs and cross bracings, they're hollow steel tubes. If a crack breaches all the way through the wall, seawater is going to rush inside. But here's the catch. From the outside, it looks exactly the same. So how in the world do you know if a sealed steel tube is compromised and completely flooded with deep ocean water? Well, the engineering solution is completely ingenious. It's a specialized technique called flooded member detection. Divers, or ROVs, will just clamp an ultrasonic transducer straight onto the outside of the tube. You see, water conducts sound waves very differently than air does. So the ultrasonic device sends out a ping, and it gets a totally distinct response if the tube is full of water. With hardly any cleaning required, they can instantly tell if that hollow member has been breached.
And the stakes here are absolutely massive. These structural tubulars are engineered specifically to be air-filled so they maintain their buoyancy and strength. If just one floods, it loses a huge amount of its resistance to buckling under those intense compression loads. Finding a flooded member is a glaring red flag. It tells you there is a through-wall crack and a sudden loss of strength that could threaten the stability of the entire multi-thousand-ton platform resting above it.
Which brings us to Section 5, Scour and Cathodic Protection, hitting the seafloor. Down at the very bottom, at the mudline, we run into a scary phenomenon called seabed scour. As ocean currents flow around these massive jacket legs, they accelerate and create these spinning, violent eddies. It's essentially like underwater desert winds, completely sweeping the sand and sediment away from the structure. If nobody intervenes, this scour can wash away up to 4.5 meters of the seabed, which leaves the foundation piles exposed and dangerously weakens the rig's footing. To fight off this underwater desertification, engineers rely on two main tricks. First, they can do rock dumping. And yeah, it's exactly what it sounds like, precisely dropping tons of heavy, graded rock around the foundation to armor the seabed. The second option is pinning down fibrous nylon scour mats. These mats are actually super clever. They're designed to artificially trap and hold onto the drifting sand, which naturally rebuilds the seabed over time. And for our absolute final check on the seafloor, we look at the platform's armor against rust, sacrificial cathodic protection. Look, bare steel underwater is going to corrode. It's inevitable. To stop it, engineers bolt massive blocks of zinc or aluminum alloys, called anodes, directly onto the steel jacket. A big platform might carry anywhere from 7 to 70 tons of these things. Because of galvanic action, the aggressive seawater will literally decompose these metal anodes instead of the structural steel. They sacrifice themselves, literally dying off over time so the platform can live out its full lifespan. That is the magic number. It's a critical, vital sign for the entire platform. During this final check, divers use a highly specialized tool called a bathychrometer. It measures the electrical potential difference generated by those dissolving anodes. As long as that reading stays safely above 0.84 volts, the corrosion protection is actively working. But if it drops below that, or if the anodes are eaten down to less than 20% of their original size, divers have to get down there, unbolt the old ones, and bolt on a fresh batch. So the real takeaway here is that absolutely none of these inspections happen in a vacuum. Every single wire brush stroke, every magnetic particle test, every ultrasonic ping, and every voltage reading is meticulously logged. It all feeds into a massive database known as the Structural Integrity Management System. It's essentially this comprehensive, life-saving medical chart for the platform, tracking even the tiniest defect trends over decades to ensure the structure stays rock solid. And that brings us to the end of our dive, but it leaves us with a really provocative question to think about. A lot of these massive structures were originally only designed for a 25-year lifespan, yet thanks to these intense inspections and modern engineering, many are operating way past that. So as this global offshore infrastructure continues to age, how are we going to manage decades of this critical subsea data to ensure our oceans and the people working above them stay completely safe? Thanks for hanging out with me on today's Explainer. I hope you found this hidden underwater battlefield as absolutely fascinating as I do.